So now that you have an understanding of arrays and linked lists, we can build on this foundational knowledge to look at some other critical data structures. A queue is a first in, first out, or FIFO, as we like to say, waiting line. We add elements to the back, and we remove elements from the front, or the head. And we repeat as needed. Although we could implement a queue with a linked list or an array, Java's array deck is more efficient. An array deck is backed by an array. And the backing array's length is initially set to 16, and its length is doubled each time the current length is inadequate. And this gives us a big O of log n for adding new items. So let's take a look at this circular array. It links opposite ends to themselves, right? So the pointers identify the current head and tail elements. Adding increments the tail pointer, and deleting increments the head pointer. So here's another way to look at it, right? So if you think about it in a circle, as we remove things, the front pointer is going to move this way. And as we add things, the back pointer is going to go this way. And once we exceed our capacity, once we fill up all the items, then this ring is going to double in size and keep getting bigger. And so we can search through things in a circle because our index, instead of hitting the end, will just go to the front after we're done. Okay. So to access Java's deck interface and the ArrayDeck class, we use the import java.util.star for queues and array decks. So let's look at a fictional Chipotle queue as an example. So see here we're porting in our java.util.star, and we could specify, an array deck or a queue specifically, but we're just going to grab the whole utility package. And so here we have a served person string, we have a queue of strings called Chipotle queue, and we're going to use an array deck to support. And so we're going to add Alexa, and we're going to add Carolyn. And while the Chipotle's queue is not empty, we are going to serve the person, which means we're going to remove them from the queue. And then we're going to ask them, hey, what's your order? So it's just like people lining up in line at a register, right? So if we compile it and we run it, here you can see, hey, what's your order, Alexa? And what's your order, Carolyn? So that's how the queue will work. I want to take a moment to actually go back and look at the Java docs, because that's something we haven't done in a while. If you look at the interface for queue, which you can find, I'm on version 9, and we're looking at queue, right? We can see that queue is an interface, as we've talked about, and E is just the element, or the type of elements that are going to be held in the queue. And you see here we've got a couple different things saying all super interfaces and all known sub interfaces. Well, a super interface is an interface that are in the ancestry of the interface. So the queue interface implements the collections interface, and the collections interface implements the iterable interface. So you can see right here in our API header, public interface queue extends collection, right? Okay, well, extends means that it's a child of it, not a it's not implementing the interface. It's actually a derived class. Okay, we're going to talk about that I believe next chapter. So but for now, just be aware that when you see super interfaces, those are interfaces that are above it, and all sub interfaces are interfaces that implement or are child of this interface. So if we look at, if we look at the deck, right, we see that it extends the queue. So it means that it is a child of the queue. And so it's going to do everything that the queue can do and more. So hopefully that makes sense. If not, we're gonna talk about it next chapter, so don't worry. But here you can also see all of the known classes that implement this interface. So each one of these classes, at a minimum, does the following. It offers add, offer, remove, poll, element, and peek. Well, what are the difference between all these? Well, these methods right here throw in an exception, and these methods will return a special value. And which one you do depends on the same thing. So both add and offer will insert an element into whatever collection that is implementing this interface, right? But offer needs to return a special value, usually of -1 or false if it can't be done, and true if it can be. So like right here, the offer method inserts an element if possible, otherwise returning false. So you can see that it differs from the .add method, which can fail to add an element only by throwing in an exception. And we're going to talk about exceptions in a couple weeks. But just so when you're looking at the different methods that are available to you, it's important to understand the difference between what an add does and what offer does, or what remove does, or what poll does. It's also important if you're looking up, if you're using an IDE that has autocomplete, where so say you are using a queue or something, a class that's implementing the queue, and you hit the dot button, it's going to pull up a list of methods that you can utilize. Well, it's important to know what these actually do. So it never hurts to go out and actually look at the documentation and learn how to read it. And if you're having difficulty reading a paragraph and saying, okay, I'm not quite sure what that means, ask me. Say, hey, you know, Corey, what does this say right here? What does this mean? And I'll be more than happy to assist. But don't be afraid to dig into the documentation to figure out something, because there's a lot of things that are there that A, I don't have time to cover in class, and B, will just help you to become a better programmer. Now, a stack is a little bit different from a queue in that it is a last in, first out storage container. So we add things or push elements onto the stack, and we remove them or pop elements at the top of the stack. So for example, here is a stack after pushing elements A, B, and C onto it, right? So you can see how the top of the stack moved as we added elements onto it. We can then perform a pop operation. Notice how we don't specify an index. We can only remove the top element. So it doesn't require us to pass in an index, right? So now we can do another push operation. Right? So we added D to the stack. So finally, to clear the stack, we have to perform 3 more pop operations. So the only way we're going to get to A is if we pop off everything that's on top of it. Just like that. So that's a stack. And so this is actually, when we talk about programs running and we talk about things being put onto the stack, this is exactly what's happening. As you call different methods, they are going onto a place in memory called the stack, and it's going to execute everything. And when the method that's in the memory calls other methods, those get added onto the stack as well. And that's how the program keeps track of what it has to do, because it does everything sequentially in order by using this stack. Let's look at another example using a driveway as a scenario. So here we have driveway parking, and we've got 2 driveways. We've got driveway 1 and driveway 2, right? So maybe you can think of it as a double wide driveway, or you and your neighbor's driveway. And in it, we're going to have this method called describe driveways, which is going to print out everything that's in the driveways, right? And so what we're going to basically do is add cars to the driveway via their license plates. And then we're going to get a car. And so what the method here does is that it basically says, hey, if driveway 1 contains the license plate, we have to move all of the cars before we can get to the car that we want, right? And when we move them, we're going to push them onto the other driveway, because that's what you would do in real life, right? If, say, you're the first person to a party and you need to leave first, well, guess what? Everybody that came in after you has got to move their car to the other driveway so you can get out, right? So that's exactly what's going to happen here. So let's go ahead and compile it and run it. So here we have our driveways, and the front of the garage is over here, right? That's why I added in this little arrow to help you understand that. So if we type in license plate, and we're just going to use, we'll use letters as our license plate. So we're going to add A, right? Okay, we're going to add B. And like most sane people, they're going to load themselves into the driveway that's shortest, right? That has the least amount of cars in it because they want to pull up as far as they can. So we're going to add a C, we're going to add D, whoops. Hit enter here. We're going to add D. We're going to add E, F, G, whoops, and H. All right. So now we've got 8 cars in the driveway. Okay, we got a good party going on. And remember, the garage is here where A and B is. So if I want to get to car B, well, let's just do D. If I want to remove car D, we're going to have to move H and F from this stack, and we're going to have to push them onto the other driveway. So we're going to pop H and then push it onto driveway 1. Then we're going to pop F and push it onto driveway 1. So if I hit minus D, you see exactly that happening, right? So now only B is left in the driveway, and D is gone. H was moved onto the other driveway, and F is pushed in after it, right? So now say car E wants to move. Well, what do you think is going to happen? F is going to move, H is going to move, and then G is going to move, right? So let's try it. Minus E. And there you have it. So you can see how the push and pop methods operate on a stack using an example as a driveway to help you understand it.